Hello dear student, this is Mr. Hitesh Patel, Assistant Professor LJ Institute of Engineering and Technology. We all know that in this channel we will discuss the subject named Basic Mechanical Engineering. Today in this video session we are going to discuss some basic heat engine cycles like Otto cycle and diesel cycle. In last video session we have discussed Rankine cycle and Carnot cycle. So let's start with the Otto cycle and diesel cycle. Okay. So first of all, we will discuss about Otto cycle. So Otto cycle was first developed by German engineer Nicholas Otto in 1876. Okay. And Otto cycle is also known as constant volume heat addition cycle. In this video session, we will discuss about the air standard Otto cycle. So first of all, what is air standard cycle? So the cycle in which air is used as a working fluid, the efficiency of the cycle is known as air standard efficiency. Okay, in air standard efficiency we are using air as a working fuel. Okay, so let's start. For understanding the Otto cycle, first of all we need to take some assumptions, that we need to understand some assumption that will be taken by Nicholas Otto. So first assumption is the working fluid must be air, that we have already discussed. Here we are find out the air standard efficiency, so the working fluid must be air. All the processes in this cycle must be reversible. Okay, the air behaves like an ideal gas and the value of Cp and Cv and gamma remains constant throughout the process. So the value of Cp for air is 1.005 kilojoule per kilogram Kelvin. The value of Cv is 0.718 kilojoule per kilogram Kelvin, and the value of gamma, that is 1.4 for air. The fourth assumption is mass of the working fluid must remain constant throughout the process. Heat is supplied from constant high temperature heat reservoir, and during this transfer there is always some amount of heat loss may occur. So this is the assumptions which taken by Nicholas Otto for understanding the Otto cycle. Okay, here you can see that this is the PV diagram of Otto cycle. In this diagram you can see that the line 1 to 2, that is the compression stroke. During process 2 to 3 heat is added at constant volume. During process 3 to 4 there is expansion of the gas takes place inside the cylinder, and during process 4 to 1 at constant volume, so hot flue gas is stored, and at constant pressure heat is rejected to the flue gas is rejected to the atmosphere. Okay, so this is the basic Otto cycle. Okay, so let's start. So during, you can see in this graph, during process 1 to 2 the air which is inside the engine cylinder is compressed. We know that when there is a compression takes place, at that time there is decrease in volume and increase in pressure takes place, and you can see in this PV diagram the pressure is gradually increasing and volume is decreasing, and during this process compression takes place adiabatically. So process 1 to 2 is known as adiabatic compression process. After compression stroke completed, at that time heat is added to the system, or heat is added to the air. After, when the heat is added to the air, at that time there is a constant volume of the air is maintained between the cylinder head and piston, so that we can draw this PV diagram like 2 to 3. At that time the volume of the air remains constant, or we can say that heat is added at constant volume during the process. Okay, after that there is expansion of the air takes place during process 3 to 4. As the air is expanded, its volume is increases and pressure is decreasing, which is indicated by line 3 to 4 on PV diagram, and this process takes place adiabatically, so it is known as adiabatic expansion process. After that, during process 4 to 1, the heat is rejected to the atmosphere at constant volume, which is indicated by line 4 to 1. So there are total 4 processes. The first process is adiabatic compression process, that is during process 1 to 2. During process 2 to 3 there is constant volume heat addition process. During process 3 to 4 adiabatic expansion process, and during process 4 to 1 constant volume heat rejection process is. Now let's discuss the efficiency of the Otto cycle. So we know that the standard equation for efficiency, that is thermal efficiency, eta is equal to net work done divided by heat supplied. So net work done, that is Qs minus Qr divided by heat supplied, that is Qs. So if we want to find out the efficiency of Otto cycle, then we have the value of Qs and Qr. From this we can easily calculate the thermal efficiency of Otto cycle. So we know that the heat supplied takes place at constant volume during process 2 to 3. So heat supplied takes place at constant volume, and we know the equation of heat supplied during constant volume process, that is mCv T2 minus T1. But in this process the heat supplied takes place during process 2 to 3. So equation of the heat supplied Qs will be mCv T3 minus T2. Okay. Next is heat rejected. So we have already discussed that the heat is rejected at constant volume during process 4 to 1. So the equation, and that is also constant volume. So the equation for the heat rejection is mCv T4 minus T1. Okay. Now net work done W is equal to Qs minus Qr. If we put these values in equation, we will get eta is equal to Qs minus Qr by Qs, and the final equation will be 1 minus Qr by Qs. By putting the value of Qr and Qs, we get the equation as 1 minus mCv T4 minus T1 divided by mCv T3 minus T2, and mCv term cancelled. So the final equation will be 1 minus T4 minus T1 divided by T3 minus T2. Now if we want to solve this equation, then we must have the value of T1, T2, T3 and T4. So we will find the value of T1, T2, T3 and T4. So we will take process 1 to 2, that is adiabatic compression process, and we know the relation between temperature and volume, that is T2 by T1 is equal to V1 by V2 raised to gamma minus 1, and we know that V1 by V2, that is compression ratio R. So we can rewrite that equation as T2 by T1 is equal to R raised to gamma minus 1. Okay. So the equation of T1 will be T2 by R raised to gamma minus 1. Now we consider process 3 to 4. So the relation between temperature and volume during adiabatic expansion process, that is T3 by T4 is equal to V4 by V3 raised to gamma minus 1, and we know that V4 by V3 is also R. So the equation becomes T3 by T4 is equal to R raised to gamma minus 1. So equation T4 is equal to T3 by R raised to gamma minus 1. By putting the value of equation number 2 and equation number 3 in equation number 1, we get eta is equal to T3 by R raised to gamma minus 1 minus T2 by R raised to gamma minus 1 divided by T3 minus T2, and we can clearly see that the term T3 minus T2 gets cancelled, and 1 minus 1 divided by R raised to gamma minus 1 is a common term. So final equation will be eta is equal to 1 minus 1 divided by R raised to gamma minus 1, where R is compression ratio, gamma is adiabatic index. From this equation we can clearly say that the efficiency, air standard efficiency of the Otto cycle depends on the compression ratio. Okay, so this is all about the air standard efficiency of Otto cycle. We will next discuss diesel cycle, air standard efficiency of the diesel cycle. So first of all, the diesel cycle was developed by German engineer Rudolf Diesel, and this cycle works at constant pressure cycle, or this cycle is also known as constant pressure cycle, because in this cycle the heat addition takes place at constant pressure. So this cycle consists of adiabatic compression process. After that the heat is added at constant volume. After that adiabatic expansion process. After that the heat is rejected at constant volume. Okay, so these four processes consist by diesel cycle, which you can clearly see in this diagram. During process 1 to 2 the air is compressed adiabatically, so it is known as adiabatic compression process. During process 2 to 3 the injector inject the diesel in fine atomized particle form in actual cycle, but in air standard cycle the heat is supplied at constant pressure, that is indicated by line 2 to 3 on PV diagram. After that there is expansion of the air takes place, due to that the pressure is decreased, volume is increased, and after that the heat is rejected during process 4 to 1, that is constant volume cycle. Okay, so let's discuss the air standard efficiency of the diesel cycle. So first of all we have the standard equation that the thermal efficiency eta is equal to net work done divided by heat supplied. Net work done, that is QS minus QR by QS. So if we have the value of heat supplied as well as heat rejected, then we can easily calculate the thermal efficiency of diesel cycle. So heat supplied QS is equal to heat supplied takes place at constant pressure. So the equation for the heat supplied during constant pressure process is mCp T3 minus T2. Okay. Now heat is rejected at constant volume. So the equation is mCv T4 minus T1. Now the standard equation we already knew that eta is equal to 1 minus QR by QS. By putting the value in this equation we get 1 minus mCv T4 minus T1 divided by mCp T3 minus T2. M term gets cancelled and the final equation will be 1 minus T4 minus T1 divided by gamma in bracket T3 minus T2. So for if we want to solve this equation, then we must find the value of T1, T2, T3 and T4. By putting all this value in this equation, we will get the actual equation for the air standard efficiency of diesel cycle. So first of all we will consider process 1 to 2. During this process there is adiabatic compression takes place, and we know that the relation between temperature and volume during adiabatic compression is T2 by T1 is equal to V1 by V2 raised to gamma minus 1, and we know that V1 by V2 is the compression ratio R. So T2 is equal to T1 into R raised to gamma minus 1. Now we will consider process 2 to 3. So process 2 to 3 is known as constant pressure process, and we know that during constant pressure process the pressure term remains constant. So the relation between temperature and volume is T3 by T2 is equal to V3 by V2, and we know that V3 by V2 is known as cutoff ratio rho. Cutoff ratio is defined as the ratio of the air after volume of air after heat supplied and before heat supplied. So we are supplying the heat between process 2 to 3. So before heat supplied the volume of the air is V2 and after heat supplied it is V3. So the cutoff ratio is the ratio of V3 divided by V2. So we can write down V3 T3 by T2 is equal to V3 by V2 is equal to rho. So final equation T3 is equal to T2 multiplied by rho, that is equation number 3. Okay. Next we will consider process number 3 to 4. During this process there is adiabatic expansion of the air takes place. So the relation between temperature and volume during adiabatic expansion, that is T4 by T3, that is V3 is equal to V3 by V4 raised to gamma minus 1, and we know that V3 by V4 is equal to rho by R, and we can rewrite the equation as T4 by T3 is equal to rho by R raised to gamma minus 1, and we can rewrite this equation as T4 is equal to T3 into rho by R raised to gamma minus 1. So T4 is equal to, by putting the value of T3 in this equation we get T4 is equal to rho raised to gamma into T1. By putting the value of T2, T3 and T4 in equation number 1, we get the equation is eta is equal to 1 minus gamma in bracket T1 into rho raised to gamma minus T1 in divided by T1 into rho r raised to gamma minus 1 minus T1 into r raised to gamma minus 1. From denominator and numerator we get T1 as common, so we will get the next equation as 1 minus 1 divided by r raised to gamma minus 1 rho raised to gamma minus 1 divided by gamma in bracket rho minus 1, and this is the equation of air standard efficiency for diesel cycle. From this equation we can clearly say that the air standard efficiency of the diesel cycle depends upon the compression ratio as well as cutoff ratio. So if you have any queries in this theory, then you can write down your comment in the comment section. Thank you for watching my video.